perfect segue into the final session of the day because you used Biolearn. Thanks. Or you used the challenge data set. It's amazing. So good evening. I'm Dane Gobel, co-founder of Methuselah Foundation and part of the Biomarkers of Aging Executive Committee. Before we jump into the last session, I'd just like to briefly say thank you to everyone for coming. And I'm very happy and honored to be part of this initiative, which I really feel is a profound shift in the energy and intended direction of the field as a whole, and it's really very, very gratifying to see it happening. So as everyone here knows, there is a major bottleneck in the field, and that is the lack of validated biomarkers of aging. So I think it's fair to say that in order to speed up progress in terms of regulatory adoption and gerotherapeutic development, we need endpoints, we need biomarkers. So a couple of years ago, we put our heads together and started thinking about how we might start applying open science and open innovation approaches to that problem to address that bottleneck. And so we began developing a collection of software tools and an open innovation challenge and data set. And so we thought we'd take this last session to share a little bit about that, and then also to give some awards to the amazing folks who actually participated in this effort. So just as a quick rundown of how we're going to do this, we're going to start out with Albert and Seth, who are leads on the Biolearn library, to share a bit about the tool set and the challenge that we developed. Then we're going to have some of our friends from Bayer talk about their work with translational biomarkers of inflammaging. And then we're going to close with the awards for phase 1 and phase 2 of our Biomarkers of Aging Challenge. And then maybe we'll take a nap. So without further ado, please welcome Albert Ying from the Gladyshev Lab as he kicks off our open science discussion.
Thank you for the introduction. And I'm Albert Ying. I'm a graduate student in Harvard Medical School right here and in Vadim Gladyshev Lab. And today I'm going to talk to you about our work on systematic evaluation and curation of aging biomarkers. Great. Great. Okay. So in the past years, we have been working on this open platform, we call it Biolearn, which is really trying to make a centralized platform for both aging biomarker and the human data set. So basically what we did is that we curated over 20 different human data sets, including many large cohort, and recently we're also working with very famous large cohort like Generation Scorden or also MESA, etc., to basically standardize their data set and allow them to easily be run, to be used for training for new clock or evaluating our published clock. And we also curated more than 30 different epigenetic-based biomarkers in the platform. And just a showcase on what we can do with this kind of standardization and curation. So this is just one example. Here we show you how did we do this benchmarking on the accuracy of chronological age for a published clock. So here I'm showing you the result of benchmarking for over 15 different published biomarker on 8 different human data sets in Biolearn. So you can really see that we can really profile like how different clock can perform in different kind of data set. And you can see the top performing clock is really the Horvath version 2, which is the Horvath skin and blood clock, and followed by Hannon, and followed by Horvath version 1. And I really want to highlight that it's really how easy it is to run this analysis. So you can see the right top side, just with one line of code, you can load in any data set currently curated in Biolearn. And with another 2 lines of code, you can run any clock currently in Biolearn on this data set. And beyond chronological age, we can also assess how different clocks perform in predicting mortality in different data sets. So here we just show an example with 2 cohorts. The first is the NAS, which is a normative aging study cohort, and another is our own MGB cohort. So you can really see that how different clock can perform differently in different cohorts. And beyond the, do I have a mouse? So it's supposed to be a video, but I don't have a mouse. So basically, oh yeah, thank you. So beyond the mortality, we're also curious how different clock can be associated with different kind of disease or multi-morbidity. So you can see like it's really kind of dynamic. So different clocks really good at predicting different kind of disease. So I think this is really important to do, like to benchmark the ability of different clocks in predicting different kind of disease, And mortality, this is important information for you, like before you're choosing what clock to use and decide how to interpret your clock result. Oh, yeah. So community is really using our Biolearn package. So in the past 6 months, the Biolearn package is downloaded over 15,000 times. And if you happen to do so, I encourage you to download it from our link or through its QR code. So it's a GitHub. It's totally open source. It's a GitHub repository. We have a very detailed tutorial, and feel free to look at it. And in the last part of Biolearn part, I will just give you one more example on how we use Biolearn in enable really amazing studies. So I'm kind of biased, it's my own study, but basically we built a large database called Clockbase, where we're trying to really analyze all the data in the public domain. So we collected 500,000 data set, actually from 50,000 data sets from Geo with over 2 million samples. And with Biolearn, we can really just profile all the epigenetic clock on those 2 million samples, and we have all these clock measurements. The idea is that in all the intervention people tested before, like maybe some people study hair loss, maybe they test some compound, and maybe those compounds can really reverse aging, just we don't know yet. So with this analysis, we can really try to find all this intervention hidden in the data set. I call it a mega scale search for intervention. So if you're interested, we also have a preprint here. We also publish our data on the Clockbase website, which is you can consider as a database. So feel free to look for it. Okay, and for Biolearn, feel free to check our preprint. It's currently on bioRxiv, and there's more information how do we curate, how to end result curation. And the next part is challenge. So all of you know that we have this huge biomarker aging challenge where I have $200,000 cash prize to the winners. And but before I go into the detail, I want to first convince you why do we need a challenge? So to convince you, I'm giving you an example from another challenge that has been run for decades. It's called CASP, which is a stand for Assessment of Technique for Protein Structure Prediction. So all those protein structure prediction model, you know, like Rosetta Fold, AlphaFold 1, AlphaFold 2, they all first come from this CASP competition. And they also, like the inventor of this method also won the Nobel Prize this year. So guess what? We have another challenge here. And I don't know what happened next, but maybe, you know. Yeah, so I think now I've convinced you in just one simple slide. Then let's talk about when and how. So this is a timeline of our challenge. So we really started promoting our challenge in the end of last year. We started our phase 1 in March, which is focused on predicting mortality, chronological age. And our phase 2 is focused on mortality prediction starting in July. And our phase 3 will be house band. Seth will introduce more on our phase 3. To really enable a challenge, we really trying to make our own private cohort so other people don't have access to it. So for now, this will be open source later. But so basically, we'll have a local cohort from MGB Biobank with 500 people with very diverse genetic background and also very nice distribution of age. And we did the epigenetic methylation profiling for them and use them as a cohort for the challenge. So here I'm presenting you the result of the phase 1 challenge. So in the left side, you see a bar plot. They're colored by the category of clock. So the red clocks are the published clock. So as expected, like similar to our previous benchmarking result, the top performing clock are Hannah and Harvard's version 2. But all of our challenge clock, which submitted by our participant, outperformed the public clock in last round. So all of our participants in the last round, they achieved the accuracy of within 2.5 years, and especially our top ranking result. And again, I want to congratulate and thanks to all the participants, and especially our winners for phase 1 with Julian, Lucas, Jacob, and Stefan. And without them, will be no challenge and no winner. So thanks. Yeah, and for challenge, we also have a preprint. We submitted like 4 days ago, but something's wrong with bioarchive. But it should be online anytime. Yeah, so stay tuned. Yeah. Okay, I will use my last 2 minutes to talk about, if I still have 2 minutes, to talk about something about the evolution of biomarkers of aging, which is I'm working on in past 5 years during my PhD. So within this year, we really witnessed some training of the biomarker of aging, either from us or from our collaborator or other people in the field. So the first is that thing I noticed is I call it embrace the higher dimensionality. So earlier this year, we have our causal clock published, which is really 2 clocks. The 1 clock measuring damage, and we call damage, and 1 clock measure adaptation, which is measuring adaptation. And then late last year and also this year, basically 2 papers, one from Tony West-Corey's lab and another from other lab, really show that we can build organ-specific clock based on plasma proteome data. And it's literally just 1 clock per organ. And also there's a system age, which is from Seagal in Albert Ying-Chen's lab. Basically similar to organ age, but it's one clock for one of your organ system. And last month we released our new framework we call Agium, where we really built like almost 2,000 different aging clocks, with each of them trying to measure the aging of different biological process. So I think the message is that aging as a complex process is really shouldn't be represented by a single number as a single biological age. I think in the future we'll see more and more approach like this to really trying to profile aging with a higher dimension as a distribution. Okay, my second and my last point is large model. So this is one work from our collaborator, Alex Jankowski, earlier this year. It's Precious 3 GPT, which is a large language model approach that really trying to use this large language model architecture to study, to understand the differential expressed gene or methylation profile for different kind of intervention. And also this month, Lucas also have this CP-GPT, which is foundation model for DNA methylation. And guess what? We also have a foundation model for DNA methylation. And I think in the future we will see more and more this kind of large language model, and I think a breakthrough in the AI field and all other fields will eventually contribute to aging. And with this, I want to thank you, and I want to introduce you to Seth.